So we will now prove this important theorem. It's called the Banach-Alaoglu theorem. Okay. So V Banach B star, the closed unit ball in V star, is weak star compact. Okay, so proof. So closed unit ball in infinite dimensional space is not norm compact, and we are saying that it is weak star compact. Okay, so first we define the product space capital X equals pi x belonging to V of minus norm x to norm x. For every x you have this interval, and then you have the product space with the product topology. So this is each interval is a compact interval, and therefore product of compact spaces by the Tikhonov's theorem, X is compact. So X is compact. Okay. Now let F belong to B star. Then mod Fx is less than or equal to norm Fx, norm F into norm X. Norm F is less than or equal to 1, so which is less than or equal to norm X. Therefore Fx belongs to minus mod X minus norm X, so Fx belongs to the interval minus norm X to norm X. So given any so from B star to X, I define a map phi. So we have phi of F whose xth coordinate is nothing but f of x. So since if two functionals agree at all points, then they have to be the same functional, so this implies that phi is 1, 1. Okay, so phi is a bijection from B star on to its image phi B star. Now you look at the topologies. What is a product topology? Product topology, typical open set, looks like open in a finite number of the x's, and the rest of it is the full thing. Okay, so that is the definition of the product topology. So you have minus epsilon I to minus epsilon to epsilon in a finite number of ones, and then you have the rest of it can be open. And so if you look at the weak star topology, what is that? It is set of all f such that f minus f naught is precisely at xi is less than epsilon for finite number of i's. Okay, so this is exactly the topology there. So the definition of weak star topology and product topology on X imply that phi is an isomorphism or homeomorphism. Therefore, we just have to show, so enough to show phi of B star is closed, because a closed subspace of a compact set is compact. So if phi of B star is closed, then phi of B star will be compact, and since phi is a homeomorphism, you have that B star will also be compact. Okay, so we just realize that the product topology, which means a finite number of sets are open for a finite number of x's, and that's exactly how the weak star topology is also defined. Okay, so that is the observation which we make. Okay, so now let us take any epsilon belonging to 0. Okay, before that, so we have to show that this is closed. So let us take f sub x, x in V. So this is in the product space which belongs to phi B star, closure. Okay, define f of x equals f sub x. Then what do you know? Mod fx is less than or equal to norm x. Okay, so to show fx, x in V, belongs to phi B star, enough to show f is linear. If it is linear, this condition already tells you it is continuous, and therefore it's the image of a continuous linear operator, continuous linear functional under this mapping phi which we have defined here. So we just have to show that phi is, f is linear. Okay, so how do we do that? So it is in the closure, therefore there exists a G belonging to phi B star such that G lies in any neighborhood of f. Okay, so such that, so I am going to take a neighborhood, namely consisting of 3 points x, y and x plus y. So we take g of x minus f of x is less than epsilon by 3, mod g of y minus f of y is less than epsilon by 3, and the third point I am going to take g of x plus y minus f of x plus y is less than epsilon by 3. Okay, so I have taken 3 points x, y and x plus y and taken epsilon by 3 neighborhoods around f of those points, g of those points, f of those points, sorry, and then that gives me a weak star neighborhood, and that weak star neighborhood must intersect phi of B star because the given function is in the closure, and therefore I can find such a G. Then what do you know about f of x plus y minus f of x minus f of y? So you add and subtract the g's. Since g is in phi of B star, we know that g of x plus y equals gx plus gy, because g is in phi of B star. Okay, so therefore this is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. This is less than epsilon, and this is true for all epsilon. So this implies that f of x plus y equals fx plus fy for all xy in. Similarly, we can prove f of alpha x is alpha times f of x. Same way, you produce a g and then that is very small by mod alpha etc, and then you can do it. So this implies that f is linear and continuous, and therefore implies f belongs to phi B star. Therefore phi B star is closed, hence it's compact. Phi is an homeomorphism, therefore B star is also compact. So this proves the Banach-Alaoglu theorem. So this is the advantage, as I said, by going to the weak star topology, the open sets become fatter and they are fewer, and therefore the chances of a set being compact are better, and in this case we see that the closed unit ball, which won't be compact in the norm topology, is now compact. Okay, so now we have a lemma due to Helly. So V Banach and Fi in V star 1 less than equal to I less than equal to n, and alpha I scalars again 1 less than equal to I less than equal to. The following are equivalent. One, for every epsilon positive, there exists an x epsilon in V such that norm of x epsilon is strictly less than 1, less than or equal to 1, and mod Fi of x epsilon minus alpha I is less than epsilon. That means I can approximately, I can find the x epsilon such that the Fi of x epsilon approximate the alpha I as closely as I wish. Okay, so that is the thing. The second condition, which is equivalent to this, is that for all scalars beta I 1 less than equal to I less than equal to n, you have sigma alpha I beta I equals 1 to n is less than or equal to norm of sigma alpha I, beta I. Beta I F. Okay, so this inequality guarantees the existence of an x epsilon which approximates at each Fi alpha I as closely as we wish. Okay. So proof. So let us show that 1 implies 2. So you let S be equal to sigma mod beta I. Then by 1, what do you have? Mod sigma I equals 1 to n of beta I Fi at x epsilon minus beta I alpha I. This will be less than or equal to Fi x epsilon minus alpha I in modulus is less than epsilon, and therefore that comes out. So you get this is less than epsilon times S. Therefore you have sigma mod sigma beta I alpha I equals 1 to n is less than or equal to epsilon S plus sigma mod beta I Fi of x epsilon, but that is less than or equal to sigma norm of sigma I equals 1 to n beta I Fi. Because beta I Fi of x epsilon in modulus is less than, that is sigma beta I Fi of x epsilon, and that is less than sigma norm of beta I. Okay, okay, so this implies 2. So, and this is true for all epsilon, so we can let epsilon go to 0, and then you get the second condition. Okay. Now we want to show that 2 implies 1. Yeah. So you pose alpha bar equals alpha 1 to alpha n. This is a vector in Rn, and you, or Cn if you like. Okay, we will do it with Rn. A you define from V to Rn in the usual way. We are going to define A of x equals F1 of x, Fn of x. Okay. So what do we need to show? We need to show, if you look at the condition 1, what is it saying? You should be able to find x epsilon less than or equal to 1 such that Fi of x epsilon is less than as close to alpha I as you like. That means we have to show that alpha bar belongs to A of B closure, where B is the closed unit ball. Okay, so if not, you have A of B closure. Now that is a convex set, closed convex set, and you have alpha bar, which is a single point, which is a compact convex set. Therefore, by Hahn-Banach, we can find there exists lambda and beta 1, beta n. These scalars come from the linear functional on Rn. Okay, so this is linear. We have done this kind of argument before, such that sigma I equals 1 to n, beta I alpha I. So this is the action of this linear functional on alpha. So that is there is strictly bigger than, you can strictly separate, and that is bigger than sigma I equals 1 to n beta I fi of x for every x in B. And therefore, from this you get that norm of sigma beta I fi, because that's the supremum of these beta I fi of x over for all x in B. That will give you the norm that is less than or equal to lambda, which is strictly less than sigma beta I alpha I. And that is a contradiction of the statement number 2, because we are assuming 2, it just goes the other way around. Okay, so that proves this proposition or lemma. So now we have a proposition. It's interesting. So V Banach, B is the closed unit ball in V, and B double star closed unit ball in V double star. J V to V double star canonical mapping. That means what? Jx of f is f of x. This is how we studied reflexivity and so on. So this is the canonical mapping. Okay. Then V double star is the weak star closure of JB in V double star. Okay, so proof. So B double star is the closed unit ball in V double star. V double star is already a dual space, and therefore this is weak star compact by the Banach-Alaoglu theorem. Okay. Therefore, it is weak star closed. Now you take phi naught in V double star. And so we have to show that every weak star neighborhood of phi naught will intersect JB, because that's what we mean by showing that it is dense, because then that will make B double star to be in the closure of JB, but B double star is already weak star closed, and therefore it is in fact the weak. So enough to show every weak star neighborhood of phi naught intersects JB. So let us take a U, which is a weak star neighborhood. So what is this? This is such of all phi in V double star such that phi minus phi naught evaluated at Fi. So you have to go to the space which gave you, whose dual is V double star. V double star is the dual of V star, and therefore we have to take this less than epsilon. Okay. 1 less than equal to I less than equal to n, where Fi belongs to B star for 1 less than equal to I less than equal to. So this is the standard neighborhood of this point. Okay. So let epsilon be greater than or equal to 0, and let us take, that is given of course, and then let us take alpha I is phi naught of Fi. Then if beta I 1 less than or equal to I less than or equal to n arbitrary scalars, then what can you say at sigma beta I alpha I equals 1 to n. Modulus of this is equal to modulus. What is alpha I? Phi naught of Fi. So this is equal to modulus of phi naught sigma I equals 1 to n of beta I Fi. Okay, and phi naught is in B double star, so its norm is less than or equal to 1. So this is less than or equal to norm phi naught, which is less than or equal to 1 into norm of sigma beta I Fi. So this is less than or equal to 1. I forget this. So I have this inequality, which is the condition 2. Okay. So this is equivalent to saying there exists x epsilon such that Fi x epsilon minus alpha I is less than 1. Now what is, so there exists, so by Helly there exists x epsilon in V, norm of x epsilon is less than or equal to 1, and mod Fi of x epsilon minus alpha I is less than epsilon. That means what? That is j x epsilon of Fi minus phi naught of Fi is less than epsilon for all 1 less than or equal to I less than or equal to n, and that is j x epsilon belongs to U. Okay, and it also Jx epsilon is where it belongs to phi of B. So Jx epsilon belongs to phi B intersection U, and that proves the result. Okay. So what is the meaning of this result? So assume V is reflexive. Then of course J of B is equal to B double star. If V is not reflexive, J is an isometry, so J of B is strictly contained in B double star, and J of B is norm closed. So in fact it is therefore, since it's norm closed and convex, so it's also weakly closed. But JB closure in the weak star topology is B double star, and therefore JB is not weak star closed. Okay, so we have this another example of a set which is weak star, which is norm closed and weakly closed, but it is not weak star closed, because we are again in a non-reflexive space. That means automatically in infinite dimensions. Okay, so this is about the weak star topology. So the next lectures we will look at the applications of the weak and weak star topology to the theory of Banach spaces.